All right, class, this is Algebra 2, Lesson 7.1. We start this chapter here, basically involving radicals and some other aspects. And so we need to refresh your memory of all the aspects of radicals. All right, so let's get going here. Let's start off with some basic terms. If you look off to the right here, hopefully you'll understand and remember what everything is. And so first off is the radical sign. The radical sign. A lot of people call it the square root symbol, but remember, square root is only one of the possible roots, and so the symbol itself is a radical sign. Right? So we got the radical sign. And the radical sign indicates the operation of taking a root. The operation of taking a root. So just like addition is an operation, multiplication is an operation, taking the root is an operation. So it's something you do to something. The operation of adding, you add things up. The operation of taking a root, you take the root of something. All right, and so the next is, the key is what's underneath that radical sign, and what's underneath is called the radicand. Radicand. So it starts off like radical and ends up with, instead of the L and ND in its place, radicand. And so here to the right, the X is the radicand. Everything that's underneath the radical sign is the radicand. And it's what you take the roots of. I know that's not the greatest English, but that's the point. The radicand is what you take the root of. Now, don't neglect what might be in the crevice of the radical sign, because what's in the crevice is called the index. So C here is index, and remember the index tells you what kind of root it is. The index tells you what kind of root it is. And so because the reason a lot of people say the symbol is a square root symbol is that if no index is shown, so this situation, okay, there's no index shown. All right, so let's suppose we had a problem like this. All right, the radical sign has no index shown. Well, we know that the index is 2, and it's a square root. So we just don't happen to show the 2. Just like you don't show a 1 exponent for variables or a 1 coefficient, right? We don't show those because we know they're there. Well, same thing here. We don't show the 2 because we know it's there. All right, all this basic stuff and really stuff we've learned in the past, and so I don't want to belabor those points. All right, number 2. Let's take a look at some of the aspects of what's going on here. What we need to begin to do is we need to be able to associate. Oh, that was interesting. We need to be able to associate exponential form with radical form. Exponential form with radical form. So let me get back where I was here. All right, so what we need to do is associate exponential form with radical form. Okay, so here's where we're at. If a to the n equals b, then a, right, a is the nth root of b. A is the nth root of b. Next chapter, we're going to deal with logarithms, and we're going to see this come to fruition as well. All right, so a to the n equals b is a is the nth root of b. Or all the way to the right, I can say a equals nth root, so n is my index, of b, so b is my radicand. So a to the n equals b is the same as a equals the nth root of b. Okay, I know that's a little tricky, but that is the case. So for example, if you got 2 cubed equals 8, then 2 is the cube root, cube because of the 3, right? Then 2 is the cube root of 8, or we could say this, 2 equals the cube root of 8. Okay? 2 equals the cube root of 8. Next example, x to the 4th power equals 16. Then what we're saying is x is the 4th root, right, of 16. And again, we could write that as x equals the 4th root of 16. All right? So we got to begin to get in our thinking the relationships here, and I'll show that more to you in a little bit, but that is the situation. Okay. All right. B. When n, the index, all right, so we're talking about the index, the number in the crevice, tells you what kind of root. When n, the index, is even, the radical sign indicates non-negative or the principal root. The principal root. Okay, so here's what I mean. If you've got the square root of 49, remember, square root, the index is 2. Therefore, a square root is what number times itself 2 times equals the radicand of 49. So that's what the square root of 49 means. What number times itself 2 times? Remember, the index is 2, but it's not shown. What number times itself 2 times equals a 49? Now, the principal root answer is 7. And why? Because 7 times 7 is 49, right? 7 times itself 2 times gives you the radicand of 49. So 7 is the principal root, but technically there's also the possibility of negative 7, because negative 7 times negative 7 also equals the radicand of 49. But again, when we're talking about the principal root, we only care about the positive part of that, and therefore we say the answer is 7. Okay? Just the way it is. And this is for even indexes. A square root, a 4th root, a 6th root, an 8th root, etc. All right? Odd's a whole different situation. It's a different scenario. And I'll show you that here down below in a moment. All right, so when we have the 4th root of 10,000, we're asking what number times itself 4 times equals the radicand? And the answer to this is 10. Why? Because 10 times 10 times 10 times 10, 10 times itself 4 times, is indeed 10,000. Okay? But the answer is 10. Principal root solution. Technically, negative 10 is also true, because negative 10 times itself 4 times is also 10,000. All right? So let's see if we can look at a chart here and see if we can understand some things involving that concept of roots here. All right, so let's take a look at some things. Radicand is greater than 0, meaning the radicand is positive. So if you look at the examples below here, let me scroll up a little bit more and just get rid of everything else so we can focus our attention. You look down below, there's a positive radicand, right? 0.64, it's greater than 0, positive radicand. And, oh, it's going to keep doing this to me. And then this one as well, right? 9/4, that's a fraction. 2 1/4, that is also a positive radicand. All right? The first 2 examples are negative. So what are we talking about? Positive radicand. All right. So you got a radicand that's greater than 0. If it's an even index, you get 1 positive and 1 negative. 1 positive and 1 negative. If it's an even index, if you're doing a square root, a 4th root, etc. If you have an odd index, you get 1 positive solution. explain this in a moment. Second scenario, if the radicand equals 0. The radicand equals 0. Well, this is boring because the square root of 0 is 0, the cube root of 0 is 0, the eighth root of 0 is 0, the nth root of 0 is 0. So this is just one solution, and the solution is always 0. It's kind of nebulous. Math today, they want you guys to know these kinds of things. It's common sense there. Right, but what if the radicand is negative, and that would be these first two examples? Well, it matters whether the index is even or odd. It matters whether the index is even or odd. If it's an even index, then technically, again, beyond the principal root, there are two complex root answers. Two complex roots. However, if it's odd, there's only one negative root answer. I'm not big on this chart, and I won't ask it again, but it is something that the course teaches, and so hence I want you guys to have it. Okay? So let's just take a look at the problems and make a whole lot more sense of them. All right, the cube root of negative 27 asks you what number times itself 3 times equals negative 27. So if I were to factor negative 27, it would factor into a negative 3 cubed. Negative 3 times negative 3 times negative 3 is negative 27. What number times itself 3 times equals the radicand? Well, a negative 3 times itself 3 times equals the radicand. And what is the solution? Negative 3. So notice where we're at in the chart. We're at a negative radicand with an odd index, and we should get one negative root. And we did. Okay? All right, let's look at the second example. Now we have a negative radicand and an even root. So again, I'm going to do the same thing. I'm going to factor this for clarity's sake. So a negative 81 is a negative 3 times negative 3 times negative 3 times negative 3. It's negative 3 times itself 4 times. Negative 3 times itself 4 times. Now, you might think to yourself, okay, well then the answer is simply negative 3, and it's not. It is not. We don't consider this in actuality because we're trying to take an even, okay, let me explain it this way. Negative 3 times negative 3 times negative 3 times negative 3 equals positive 81. It does not equal our radicand of negative 81. So, all right, stop the presses. I goofed this one all the way up. Let me reverse course here. Duh. Okay, I can't say this. It's not true. Negative 3 to the 4th power is a positive 81. This is what I want to say. It's a negative 1 times 3 to the 4th power. There we go. All right, that's a negative 81 radicand. Negative 1 times 3 to the 4th power. Okay. What is the square root, 4th root, etc. of negative 1? That is I, and that's where the imaginary comes from. What is the 4th root of 3 to the 4th? It is 4, and you get 4i, and you get plus or minus. Plus or minus 4i is the solution to that. Where am I getting 4 from? Man, I am just killing this one. Oh, brother. All right, I hope you're with me. That's a 3, right? All right. 3 to the 4th power. 4th root is 3, so plus or minus 3i. Okay? Butchered that one. My bad. Again, that's not true. A negative 1 times a 3 to the 4th is a negative 81, our radicand, and therefore plus or minus 3i. Okay? You end up with 2 complex roots. All right, so third example is a square root. That 2 is not shown. What number times itself 2 times is 64? Well, you may not realize it, but 0.8 times 0.8 is 0.64. So what number times itself 2 times is 0.64? The answer, 0.8. All right. Now, what are we doing here? We are doing a positive, we have a positive radicand, we have an even index, so technically, again, the principal root is 0.8, but technically the answer is plus or minus 0.8. You might say, why? Because again, negative 0.8 times negative 0.8 also equals 0.64. Here's the point. Whenever you have an even index, even whether it's odd or even, technically the answer is plus or minus. Technically. All the time. And really, the only time you don't use the plus or minus is when we're just looking for the principal root, the positive root. Okay? I know that can be confusing. Why in the world did someone decide that we're just going to worry about the principal root? I don't know. All right, but technically it's plus or minus square root of 8. So our last example, again, is an even root. So technically we're going to have plus or minus as an answer, and it really is technically the answer. Now, we've already learned this fact, that you can now break this up in the square root of 9 over the square root of 4. And again, it's going to be plus minus. What's the square root of 9? 3. What's the square root of 4? 2. And this one is plus or minus 3/2. And there are 2 roots. All right, that's what it's all about. I know that can be tricky, and I'm going to muddy the water here in a little bit, but such is the case. All right, let's get back to some more quite concrete things. Product property of radicals. All right, product property of radicals basically says this: if you have the nth root of xy, you can say, or it's the same as the nth root of the x times the nth root of the y. Really, all this is multiplying radicals in reverse, right? That's all this is, multiplying radicals in reverse. So, for example, if you look right here, if you had the nth root of x times the nth root of y, if you multiplied them, you would get the nth root of xy. This is just unmultiplying or really factoring, if you want to think of it that way. Product property of radicals. And you can go either way. Well, the point is this, that if you split it up, you can then go ahead and take the roots of things. Quite honestly, we'll go past this and do a shortcut. But let me show you what I mean on the first one, and then I'll show you a shortcut on the second one. Okay, so technically, to take the root of something, you want the index to match the radicand's exponent. Okay, so let me explain that for a moment. Let me give you a couple examples here right off the bat. If I had the cube root of 8, we all know that that's 2, but the reason it is 8 is a 2 cubed. And whenever the index matches the exponent, the root is the base. Okay? So to figure out roots, if you'll just factor things, then you'll be in great shape. Okay? You can also do this. You can divide the radicand's exponent by the index. So again, really, you would have had the radicand's exponent, the 3 from here, divided by the index. And what's 3 over 3? 1. 2 to the 1 is 2. Okay? All right, we've done all this in detail in Algebra 1 and in pre-algebra. So again, I'm not going into all those minute details. We should know that stuff already, but that is it, in case you've forgotten. Okay, so what are we saying here on this first example? We're saying that this is the exact same thing. I can break this thing up into the cube root of 27 times the cube root. I got to stop with the color. It's going to take me forever. How about an n to the 6th, making it an n cubed times an n cubed, and then I still have times the cube root of z cubed. All I've done just now is broken up this radicand into giving me cubes for the exponents of the radicand. You say, but 27 isn't a cube. Oh, well, contrary, right? 27 is 3 times 9, and 9 is 3 times 3, and there's a 3 cubed, right? So watch what happens. What's the cube root of 3 cubed? 3. What's the cube root of n cubed? N. What's the cube root of n cubed? N. What's the cube root of z cubed? Z. And these are all multiplied. Final answer, 3n squared z. We've taken the cube root of 27, n to the 6th, z cubed. Now, we don't break it up like this. We just apply that right to the radicand. Just apply it directly to the radicand. So in the second example, we got a 16. Do you know what the fourth root of 16 is? Well, if you were to factor 16, you get 2 to the 4th. Okay? So what's the fourth root of 2 to the 4th? 2, right? Whenever the index matches the exponent, the root is the base. Okay? Now I have an a to the 16th. If you want to, in your mind, you can think of it as a to the 4th times a to the 4th times a to the 4th times a to the 4th. Okay? Let me show that to you. Don't write this in your notes. A to the 4th times a to the 4th times a to the 4th times a to the 4th. By the way, remember the rule x to the a times x to the b equals x to the a plus b. 4 of them, 8 of them, 12 of them, 16 of them, right? So I could split it up like that. But that's not, I don't need to do that. I could simply take the index, the a to the 16th, and divide it by, the exponent, a to the 16th, and divide it by the index 4. 16 divided by 4 is 4, and the fourth root of a to the 16th is a to the 4th. Okay? All right? And then b to the 20th would be b to the 20 divided by 4, and it's b to the 5th. And there is the fourth root of 16, a to the 16th, b to the 20th. Now, I'll show you what to do on uneven powers and such, because this will happen. All right, so number 3, it's a square root. And notice this negative right there. Whenever you have negative, and it's a square root, you're going to have complex roots. You're going to have plus or minus, and you're going to have an imaginary number I. That takes care of that negative. So you get plus or minus I. Now I got to deal with square root of 9. I've already taken care of the negative right here. Let me cross that out because I've taken care of it. What's the square root of 9? We all know that that's 3. Now how do I do this 11, x to the 11th? All right, here's how I would approach this. Make this x to the 10th times x. Isn't that x to the 11th? It is. Why did you make it x to the 10th? Because I know I can divide 10 by 2. 10 divided by 2 is 5. So this is x to the 5th, and technically I'll have to rearrange my order here in a moment. And therefore now I've just taken the root of that. And what's the only thing left under the radical sign is the x. Can't do anything with it, so I still have the square root of x. Final answer cleaned up. The imaginary number should go in the back of the coefficients. So you end up with plus or minus 3x to the 5th I times the square root of x. And there's our final answer. Simplifying radicals. We'll do a little bit more simplifying here in just a bit. All right, next concept and thought, and this one will get you confused. We, as far as I know, can remember, we've never used to teach this, and now they want you guys to deal on this. All right, so here's what they want you to do when you have variables. When you have variables, technically now you don't have a number, and you don't know whether that number is positive or negative, and so therefore there are more than one possibility. All right, what are you talking about? All right, let me just show you. Let's just write it. Okay, so B. Use absolute value when even roots, what I mean by that is an even index, right? Because the index tells you what kind of root it is. Even roots means the index is even. Use absolute value when you have even roots of even powers to produce the principal root. Even roots of even powers to produce the principal root. And this is for variables. If the result is an even power, the absolute value is dropped. Oh, man, a lot of even. All right, confusing, I understand. All right, let's see if we can sort it out. All right, so the condition is even roots of even powers to produce the principal root. So we're after just the principal root. So here's the situation. This first one is an even root, right? Because again, it's a 2 and it's not shown. And we have an even power. So therefore then, square root of 9 is 3. The square root of n to the 6th is n to the 6th divided by 2, or n cubed, right? But we need to do the absolute value. So it's 3 times the absolute value of n cubed. This is when we're only after the principal root, the positive part, and this is the way to get it to be positive. That's all this is. It's the way to get it to be positive. Okay? And to negate the negative possibility. That's what we're doing. Say why? Because variables are variables and we're trying to solve bigger things. Okay, so second scenario, we do have an even index, even root here, even power, even power, even power. So the potential is here a lot. All right, the fourth root of 1/16. You may not understand this, but 1/16 is a 1 over 2 to the 4th. Therefore, the fourth root of that is 1/2. A to the 8th is a to the 8 divided by 4. That's an a squared. Oh, look. I ended up with an even power. I don't need absolute value. Okay, with my b's. 20 divided by 4 is 5. Oh, that's an odd power. I need absolute value. And c ends up 12 divided by 4. That's c cubed. And I need absolute value there as well. So technically you would write this 1/2 a squared, absolute value of b to the 5th, c cubed. Just stick both of them in the same absolute value. And that's the principal root answer. Okay? So what's the condition? Even root, even index, with an even power of the variable, and the result is an odd power. You need the absolute value. Okay? If it's an even power, you drop it. All right, so again, we got the condition. We got an even index. 12. 12 is a 4 times 3, right? We all know the square root of 4 is 2 because a 4 is 2 squared. So I have a 2. All right, that's done. I have an x cubed, which is an x squared times x. I'm not worried about absolute value because it's an odd power. Don't have to worry about it. So square root of x squared is x. I still have an x left in. Now in the last situation, I have this quantity to the 8th power. So I have an even index, I have an even power. So again, to take the root, I'm going to divide it by 2. And I end up with n squared minus 3 to the 4th power. I ended up with an even root I don't need the absolute value. Now, don't forget, this is all still times the square root of a 3 is left in the radicand, and an x is left in the radicand. 2x times the square root of n squared minus 3 to the 4th power, all times the square root of 3x. Tricky. All right, so B is trying to tell us that when we're just after the principal root and you have variables involved, if you have an even index and an even power of the variable, and the result is an odd power, use the absolute value. If the result is an even power, you don't need to worry about the absolute value. That's tricky. You're going to have to review that if you're going to remember it. It's going to take reviewing if you're going to remember that. All right, let's just simplify the following. And again, we're taking the principal root. So when they say simplify, they mean take the principal root. So we're looking at situations. All right, number one is an even power, but the variable has an odd, so we don't have to worry about it. Okay, square root of 20. Square root of 20 is a 4 times 5. And we all know the square root of 4 is 2. Okay, that's done. Use a little color here. My n to the 5th. Again, I want a power that divides by 2. So 4 does. So I'm going to make n to the 5th, n to the 4th times n. Why? So I could divide this by 2. N to the 4th, the square root of n to the 4th is n squared. That's all I can do. Whatever else is still left in the radicand, I still have the 5, and I still have the n. Now again, notice I'm crossing things out as I use them. I'm crossing them out as I factor them. These are important little things that are going to help you to keep track of everything. You need to do that. All right, I need to get rolling. This lesson is hanging on forever. Okay, next one. Hey, be careful. Don't lose this negative sign out in front. Okay, again, I got an even power, so I got to be careful. I may need absolute value. In the first situation, I have 3 to the negative 4 over 4, right? So I end up with, when I take the root, so here, first off, before I do anything, let's get this negative out in front. Now when I take this root, I get 3 to the negative 1. I'll deal with that in a moment and simplify. All right, a to the 5th. It's an odd power, so I don't have to worry about absolute value. I'm going to go a to the 4th times a. And again, I'm going to divide that 4 by the index, right? A to the 4 over 4 is a, and I did that part, took the 4th root of that. B to the 8th is, oh, be careful, I've got an even power. I'm ready to divide it. 8 divided by 4 is 2. I get b squared. That one's done. Have an even power, don't have to worry about absolute value. And be careful now. Is there anything left in? There is. There's an a left in. So this is times the 4th root of a. It is not proper to leave any number or variable with a negative exponent. So therefore, then to finish this up, there's my negative. 3 to the negative 1 is 1 over 3 to the 1, or 1/3, times a, b squared, times the 4th root of a. That was awesome. What a problem. That's fun. That's great. What fun. Okay, and then another situation here. We've got a square root. Again, we got an even root, so we've got to be careful. If we're an odd root, we don't have to worry about absolute value at all. Got an even root. I got to be worried about absolute value. Let's take a look. All right, 3.0121. Okay, Mr. Scarfi, what in the world is that? All right, this is weird stuff. Say, I would never think of this. That's why I'm showing it to you. Believe it or not, 3 times 0.11 times 0.11 equals 3.0121. Can I take the square root of that? I can. It's 0.11. All right, that's tricky. Again, I took that number and factored it into that. All right, be careful on my second scenario here. I'm going to use my red. I have an even root. I have an even power. To take the root, I'm going to divide it by 2, the index. X to the 2 divided by 2 is 1. I get x to the first power. I get an an odd exponent, I need absolute value. Okay, I had an even index and an even root. Ended up with an odd power. I need absolute value. All right, the last one, I have an odd power. I need to make this y minus 3 quantity squared times a y minus 3, right? That would be y minus 3 cubed. And now I can take the square root of the first one and get a quantity y minus 3. Took the root of that. Took the root of that. What's left in the radicand? I still have a 3 times a y minus 3. And again, that could be further simplified into 3y minus 9. Right? And I'm just going to, for time's sake, do that. And there's my answer. That's great. It's awesome. All right, one more concept. One last concept. Okay, let me get a little higher here. My board will cooperate. All right, last thing we want to talk about is Heron's area formula. Heron's area formula. If you're trying to find the area of a triangle, hopefully you're thinking of the base formula. Don't write this. Area of a triangle equals 1/2 base times height. 1/2 base times height. And the height is commonly called the altitude. The height is the altitude. So area of a triangle is 1/2 base times height. We have no earthly idea what the height of this triangle is. We don't know. If I don't know the height, I can't use this formula. It's the area of a triangle formula, but I can't use it because I don't know the height, meaning I don't know the altitude. Therefore, we have another formula, Heron's area formula. All right, and that's what we're here to talk about. So Heron's area formula used when you don't know the altitude. And I'll put in parentheses h, the height, right? You don't know the altitude. You can't use 1/2 base times height. All right, here's how the formula goes. Let's do the right-hand part first right here. So where S, what is S? Because you can see S is in that formula 1, 2, 3, 4 times, right? S is called the semi-perimeter. It means add up the length of the 3 sides. Side A plus side B plus side C, and semi means half, and divide by 2. So it's the A plus B plus C divided by 2. That's what S is, and you got to remember that. Okay, and then the Heron's area formula is the square root of the semi-perimeter times the quantity of the semi-perimeter minus one side, A, times the semi-perimeter minus the second side, B, times the semi-perimeter minus the second side, C. Area of a triangle. Okay? So again, when are you using this? When you know the 3 sides of the triangle, but you don't know the height, the altitude. Otherwise, go the other route. So let's run the formula. All right, so to do Heron's area formula, I've got to figure out S. So off to the right here, I'm going to do S. All right, side A is opposite angle A, and it's 31. Side B is opposite angle B, and it's 52. But again, these numbers are always the 3 sides of the triangle, right? And the other number is 34. And we got to divide this by 2. So you take your calculator out, and sometimes it'll be an even number and sometimes not. Take your calculator out, and this is 58.5, value of S. 31 plus 52 plus 34 divided by 2. Okay. So now I'm going to run my formula. 58.5, so we got the square root of 58.5 times 58.5 minus 31 times 58.5 minus, what's B? 52. You can see this gets a little long, times 58.5 minus, and by the way, if you use your calculator, I would put 58.5 into my memory. Therefore, I won't have to punch that in every time. I'll just hit recall memory. All right, all of this underneath the radical sign. So you're going to multiply all this out. You can do this in your calculator. I would hit, most of your calculators, you could do the square root button first, Then you have to do a bracket, and then 58.5 times parentheses, 58.5 minus 31, close parentheses, times 58.5, parentheses, 58.5 minus 52, close parentheses, times, parentheses, 58.5 minus 34, parentheses, enter, enter, and let your calculator do the work. You should punch this in to make sure you figure out your calculator and make sure you know how to punch things in correctly. When all is said and done, your answer should be 506.2. And remember, this is area. If it would have told us inches, I'd say inches squared. If it said meters, I'd say meters squared. It doesn't say, so I will say units squared. 506.2 units squared. All right, I know that lesson's a little long. There's a lot to cover. Foundational lesson to this chapter. Some parts you may need to go back and look at. You've got your text as well to help you. And so the homework is listed there. Pay close attention to emails or info direct as to when you'll have to execute that homework. All right, it's been a long video, so I'm not going to review. You have it there for you.